Hello, everyone, and welcome to the start of Unit 4. So Unit 4 is about quadratic functions. It's a pretty long unit. We talk about a lot of stuff in here, a lot of algebra techniques, application problems, graphing, functions, polynomials. Oh, it's just chock full of just great stuff. But we're going to start off with Lesson 4.0 on factoring. This word, what does it mean to factor something, right? And if you were in class, and now you're maybe rewatching this video for saying, oh, what did I miss? You may have remembered me saying that this is one of the most important days in all of Algebra 2. Factoring is a really fundamental skill that we're seeking to strengthen and improve over the course of the year. I say, what's 2 plus 2? And you say, hey, that's 4, right? So that if I say, hey, x squared minus 10x, how do I go something here? Plus 21, what is the factor? How do you factor that? You say, oh, well, it's x minus 7, x minus 3. And you say it with just as much fluidity or, I guess, you're saying it just as fast. It comes to you just as fast as 2 plus 2 equals 4, right? And that's the goal. If you don't get there by the end of this lesson, that's fine. I'm just saying that this is something we're focusing on throughout the year. Now, I'm going to start with what this word factor means. It is a word you've heard before, but it's really important that you understand when we say factor this, what are we talking about, right? What does that mean? So your experience comes from integers. I say if n is an integer, then a, some number, right? A is a factor of n, that number, if, and you'll see this sort of notation right here, it says a divides n, like so. A divides n is how you read that. And all that means is that a divides evenly into n. So as you can read this example here, right? We say that 5 is a factor of 15 because 5 divides 15. What do we mean by that? Well, you say, 15 over 5 gets you 3. All right, so 5 goes evenly into 15. And you say, what do we mean by evenly? So when something divides evenly, you're saying there's no remainder, right? So like, for example, does 7 divide 15? I say, no, because if I took 15 and I've divided it by 7, I would get 2. Oh, I changed my little. I would get 7 into 15. I would get 2, remainder 1, right? Because I get 14 minus 1. Ooh, remember all that? Ooh, we love 4th grade. Is that what that is? I don't know. So yeah, it's dividing evenly. We don't want a remainder. Also meaning we don't want a decimal, right? When you take an integer and divide it by an integer, the hope is that you get an integer. That would mean that was a factor of it. Now, this word integer factorization is a way of expressing an integer as a product of other integers. Meaning, here's the number 20. Now, you can write this as a product of its factors. So we know that, we know that 4 goes into 20. We also know that 5 goes into 20. So we could say, hey, 20 is 4 times 5. This is called a factorization of 20. We could also say that 20 is 2 times 10. And we could also say that it's 20. Excuse me, I sneezed. I can't edit that out, sorry. I just had to bear with that. You say, bless you, Mr. Spake. So here's 20 times 1, right? That's a factorization. As a quick note, a little note. Say, note. We love little side notes. There's something called prime factorization, something you've done before. Let's say I wanted to do the prime factorization of 20. That means I would want to look at the factorization of 20 where all the factors are prime numbers. So, we said that it was 4 times 5, but 4 is not prime, right? So I would say, 4 is 2 times 2, and then you can multiply by that by 5, right? So 2 times 2 is 4, times 5 is 20. This would be called the prime factorization. Just a little tidbit. We're going to talk about that maybe in a minute here when we get to polynomial factoring. Okay, so let's move on here. So the premise is, when we say integer factorization, you're looking for integer divided by integer gets you integer. You wouldn't say like 2.5, right? Let's say, well, 2.5 times 4 is 10. This is true, but we wouldn't say that 2.5 is a factor of 10, right? Because 2.5 is not an integer, and so that's what we're looking for. Now, all this logic, and the reason I'm talking about this, Mr. Bank, I know this. I say, I know you probably know this, but everything we just sort of established there carries over for when we talk about factorizing, or as a factoring polynomials, right? So doing a factorization of polynomials is really just like factoring integers. When we say that something is a factor, as I've said like a million times at this point, an integer, 20, divided by 4, an integer, yields an integer. Therefore, 4 is a factor of 20. It goes into 20. We carry this for polynomials as well. And so the example I have written here is, let's say you have 9x squared plus 6x over 3x. And I say, well, is 3x a factor of 9x squared plus 6x? Well, 9x squared plus 6x is what we call a polynomial, and 3x is also called a polynomial. And so we would say, well, if I were to divide these and get no remainder, and I result with another polynomial, well, then that would mean that 3x is a factor of 9x squared plus 6x. Also, I keep saying this word polynomial. You might be saying, Mr. Spake, what the heck's that? I say, a quick aside for anyone who doesn't know the word polynomial. Polynomial is really, it's like an expression with variables and coefficients where the variables have whole number powers. You scratch your head, you say, huh, what? I say, look, x squared, that's a polynomial. Well, technically it's a monomial. X squared plus 2, this is a polynomial. X cubed minus 3x plus 1, this is a polynomial. X to the fourth plus x squared plus 2. This is a polynomial. Plus x minus x to the fifth. This is all polynomial, right? Put a half here. Put a 3 here. It doesn't really matter. These are all examples of polynomials because you have variables, but all the powers on those variables are whole numbers, right? If they weren't whole numbers, then they wouldn't be called polynomials. For example, if you had x to the 1/2 plus 1, that's not a polynomial. If you said x to the negative 2 minus 3, that's not a polynomial, yeah? They got to be to whole number powers. And when I say whole number, I also mean positive, right? Not just integers. So that's just a little example for you so you understand that. So back to what I was saying about polynomial divided by polynomial. Well, let's see. Let's carry out the division here. So look at my little highlighter. I say, here's 9x squared divided by 3x. So if I focus my attention on that, right, 9x squared divided by 3x, well, 9 divided by 3 gets 3, and x squared, that's 2x's over 1x, so you're left with 1x, right, because one of the x's canceled. So I'm left with 3x when I do 9x squared divided by 3x. Then I say, okay, plus, because you got to divide everything, right? Plus 6x over 3x. Well, 6 over 3 is just 2, and x over x is just 1. So it's 2 times 1, which means it's plus 2. Okay, so notice that the top was a polynomial, the bottom was a polynomial, and the resulting quotient of this division was a polynomial. How nice is that? So what is the significance of this? Well, I say, since it divided evenly into it and I got another polynomial, that means, I say, therefore, 3x is a factor of 9x squared plus 6x. And in particular, what you can do is you can say, well, 9x squared plus 6x factors as a polynomial 3x, then you say, well, times what, right? Because 3x is one of the factors. What's the other factor? I say the other factor is the quotient. It's what we got, 3x plus 2. So it's 3x times 3x plus 2. And you can see that if I were to distribute these, 3x times 3x is 9x squared, and 3x times 2 is plus 6x. Yeah? And so when we're factoring these polynomials, we're looking for essentially a product of other polynomials. So taking something like this and writing it as something times something. It won't always be two things. You could say, you could factor something with 3 terms or 4 terms, right? But the premise is that they're all going to be sort of simpler or smaller polynomials, right? They're simpler. They're less, the powers are less than what you see here. Maybe the coefficients are simpler, right? And so that's factoring polynomials. So that's all just kind of set up and understanding what are we doing, right? What's the goal here? As I mentioned, these techniques will be important for really just general algebraic techniques. The two probably most common things I see, just being a math teacher or being the person who sees students go through algebra, pre-cal, calculus, right? Factoring is going to really help you in simplifying algebra expressions, not just for quadratics, but for all sorts of stuff, especially with stuff with polynomials. And it'll also be when we're studying equations, how to find solutions. It's a good way of finding solutions to a problem. Now, in this lesson, we're covering 5 different techniques for factoring. And these are all very technical techniques. I have a separate video that's going to come after this, 4.0 continued, and that's going to show you some tricks, so some little factoring tricks you can do. These are some techniques with the sort of technical explanation as to why they work. Yeah, 5 different factoring techniques you can use when factoring polynomials. And so to go through them, right, you have factoring using GCF. We'll talk about that. Factor by grouping, factoring quadratic trinomials, difference of squares, and perfect square trinomials. Now, from Algebra 1, you should know number 1 and number 3 at a bare minimum, right? This number 1 and number 3, I am positive you did that in Algebra 1. Maybe you did number 4. Maybe you did number 5. And if you did number 2, that would be impressive. But, well, I don't know. Everyone has a different experience, yeah? So let's start with factoring using GCF, greatest common factor. GCF, greatest common factor. As a quick reminder, what is GCF? I say, well, look, let's say you had 2 numbers, 28 and 42, right? What is the GCF of these 2 quantities, or these 2 numbers, right? I said, well, greatest common factor means the highest number divisible into both, the biggest factor that goes into both. And looking at 28 and 42, knowing your multiplication tables, you might scream, 7! 7 goes into both. And I'd say, yes, correct, student. 7 does go into 28 and 42, but then I ask, I say, a little smirk. Is that with a little question mark, right? A little smirk with a little question mark. Is that the greatest factor that they both share, right? And you say, well, hold on a minute, student. Doesn't 14 times 2 equal 28, and 14 times 3 is 42? You say, 14 is also a factor of these 2 numbers, and it's the greatest one. So the idea with GCF is between your terms, you want to look for the sort of greatest number of things that they all share, yeah? And so I'll kind of go through that. You can see here in bold that it says you always check for GCF first, and this is true. Do you have to? No, but you should. It's probably it's one of the easiest factoring techniques to do, and if you have multi-step factoring, it's usually better to get GCF out of the way so you can focus on some other stuff. So Here's example 1. It says factor the GCF from the following expressions. So I've got 4x cubed minus 20x. Now, if you have pretty good numerical intuition, you've seen this before, you know what we're talking about. Maybe you skip ahead in the video, you check your answers, you see it, you're doing fine. I'm teaching this as if you've never seen this before in your life, yeah? And so if you said, I don't know what a GCF is, I don't know how to find the greatest common factor between these two things, I say, well, how about you completely factor them and then just circle everything they have in common? So for example, 4x cubed, I said, well, 4 is 2 times 2. And x cubed is 3 x's being multiplied together. This would be like a complete factorization of 4x cubed, just split into all of its simplest factors, right? And then I would have 20x. I'm not going to really worry about the negative right now. 20 is 2 times 2 is 4, and then 4 times 5 is 20. So that's, I'm doing a prime factorization here, and then there's a single x. And I say, well, okay, what do these guys have in common? It seems they have a pair of 2's in common, and then another pair of 2's, right? I guess I spoke that wrong. They have a pair of 2's in common, right? This means they share 2 and 2, and of course 2 times 2 is 4. That means they both, integer-wise, numerical-wise, they share a factor of 4. And that's the greatest integer factor they share. And look at 4 and look at 20. Well, that's the greatest number that goes in there. You say 4. I know that, Mr. Spake. Then look at your variables. How many variables do they share? Well, there's only one x shared, right? These other 2 x's do not have any other things to pair with, so it's just 1 x. So we would say that the GCF is 2 times 2 times x. That's all the product, or in other words, 4x. So the way you would factor this is you'd say, okay, here's 4x, and we're going to factor that out, because that means 4x cubed minus 20x is divisible by 4x. And if you did this, if you actually did this division, you could find the other factor. So 4x cubed over x, well, the 4x. The 4's cancel, and x cubed over x is just x squared. And then negative 20x over 4x, well, the x's cancel, and negative 20 over 4 is negative 5. So that actually means that the other factor is x squared minus 5, because 4x goes into that, but so does x squared minus 5. By the way, and I just can't help myself but tell you this, in Unit 5, we will learn, let's say I had this, right? We'll learn how to take that and divide it by x squared minus 5. We're going to learn how to do that, and you'll get the answer 4x. Ooh, it's going to be good, but we're not there yet. We're not ready for that. No worries, okay? And so I'm done. By the way, also notice, look at what I didn't circle. Why don't I switch colors here? We got a yellow here. Ooh, love it. I did not circle these 2 x's. Well, hey, that's why that's x squared. I did not circle this 5. Well, that's why that's a 5. Yeah? So if you choose to do this method of just doing all the factors, what all they have in common, that works. Yeah? Okay. I'm going to erase those little yellow things and proceed. Let's just do another. So I'm just going to, kind of go through this example. I've already explained it. So let's take 6x squared y. So 6 is 2 times 3. Then that's 2 x's and a y. And then if I do 15xy, well, 15 is 3 times 5. And then you have an x and a y. And then 9y is 3 times 3 with another y. So I say, okay, what do they got in common? Well, they got 1 3 in common, and they got 1 y in common. So the GCF would be 3y, and that's it. So I say, okay, let's take 3y, put it right here, and we're factoring it out from the expression. Now what you can do is, you can kind of do it one of two ways, right? You can first think, what would you put in this space so that when you distribute 3y, you get this. Or you can do what I kind of did earlier where you look at the division. Let me try the first way and show you that. So you say, okay, look, 3y times what gets you 6x squared y? Well, I say, well, 3 times 2 gets you 6, and then there's no x squared, so I would need an x squared. So it looks like I need to multiply by 2x squared to get that 6x squared y. And then I would say plus, and then the same thing, 3 times what number is 15? Well, I would need a 5 there. And I already have a y, so that y is good, but I still need an x. So it would be 5x. And then, of course, 3y times what is 9y? Well, you just need a 3. So it's plus 3. And so we're done. Again, you could just actually do division here, like this. If you take this and just literally divide it by 3y, you say, oh, 6 over 3 is 2, y's cancel, so it's x squared, and so forth, right? So that, there's a lot of ways you can do this. You could look at this and say, oh, it's 2x squared, 5x, and 3. 2x squared, 5x, and 3. Whatever you want, guys. It doesn't matter to me. Or you just look at it and you know, right? Or you just look at it and you know. Okay. I will do these two examples just for the sake of having them, but I'm not going to take as much time explaining because already this video is getting long, and that's fine because I love talking about math. I just love it. So I say, okay, here's a squared b squared plus ab squared. So a times b times b, a times b times b. They share an a and they share two b's, means the GCF is ab squared. So what you'll do is you'll factor out ab squared. You say, okay, well, what would be left? Well, I would need to do ab squared times something to get a squared b squared. So that's missing an a. And then, and this is what kind of gets students is, well, this is ab squared already. So do I need anything else? Is it just times a? I say, well, it can't just be times a, because if you multiply this here, you only get this. So how do you get this plus ab squared business? You say, well, ab squared times what is ab squared? Well, that's like asking 5 times what is 5. It's 1, right? You need to say plus 1 here so that that actually ends up multiplying. This times 1 is itself. And that's it. The other one, if you look at it, right, 36, and I'm not even going to do a prime factorization here. I'm just going to look. 9 times 4 times a squared. And then 9 times 2 times a, and then 9 times 3. And there's no a, right? So this shows you they all share a factor of 9, but 4, 2, and 3 don't share anything in common. I mean, 4 and 2 do, but not with 3, right? So no other stuff there. And then there's a, but then there's no a here. So the only thing they have in common is this 9. And so you'd say, okay, then that's 9 factored out, and it's just 4a squared minus 2a and plus 3. And notice I'm carrying the minus because of that minus, the plus because of that plus. And so that's GCF factoring. Okay? Okay, that's that. Let's move on. Factor by grouping. Okay. So factor by grouping, this is a fun little technique that is pretty useful especially for the higher order polynomials when we get to Unit 5. But it's also the premise and the reason why trinomial factoring works. You say, what? What's trinomial factoring? I say, hold on, I'm getting there. First of all, this idea of grouping. What is grouping? So there's this property in math called the associativity, or associative, right? Associative property for both addition and multiplication. This is what it looks like. It says A plus B plus C, see how that's in parentheses, is equivalent to A plus B plus C. It's basically saying that you can group stuff and it doesn't do anything, right? It doesn't change the fact that this addition still carries out and works. I say, well, Mr. Big, what are you talking about? I say, look, 1 plus 2 plus 3. You could do 1 plus 2 first, and then you get 3 plus 3, which is 6. Or you could do 1 plus 2 plus 3, where you say 2 plus 3 is 5, so 1 plus 5 is 6, right? That is literally all the associative property is saying. It's a way of grouping stuff together. And so what we're going to do is, using the associative property of addition, group our terms in our polynomial and then do GCF factoring on it. You say, what? I said, look, it's best explained with an example. So here's my polynomial, 2x cubed minus 4x squared, blah, 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 blah. I'm going to group, meaning sort of put parentheses around just two terms. And I'm just going to choose the first two and last two. And this usually works if the powers are in descending order, by the way. Anyway, you say 2x cubed minus 4x squared. This is the first grouping. The other grouping, so I'm going to put a little plus here. It's added with negative 5x plus 10. And looking at these groups, I'm going to do the GCF of both. So that same scale we were just practicing, but now on using this grouping stuff and then doing GCF on each group. So if I look at this one, looking at it, 2 and 4 looks like they share a GCF of 2, and then x cubed, x squared looks like they share a GCF of x squared. And the remaining thing that, if you factor that out, the other factor would be you need a single x to make that cube, and then you need to say x minus 2, so minus 2 to get the negative 4x squared. And so that one's done, right? You say, woo, got the left one. Now I look at the other group, negative 5x plus 10. And so you can look at 5 and you can look at 10, and so immediately you should say, hey, I know that the GCF is going to be 5, because 5 shares 5, 10 shares 5, and that's the biggest you could do, right? Which is true. But a little note. I say a little note. Oh, I love my little notes. A little note. If the lead term there is ever negative, factor the negative out with it. Is this essential? Not really, but I don't know. It's just what we do. It's standard. We like the lead term in a polynomial to be positive if we can make it positive. It's just standard, okay? Anyway, I don't want to get too much into that. You see that it's negative 5x. I would like that lead term, the front term, to be positive if possible. So I'm not going to factor out 5. I'm going to factor out negative 5. Okay? So negative 5 out from negative 5x, well, this would become x. And if you say 10, and you take out negative 5, meaning 10 divided by negative 5, you would need a negative 2 here. Because you need to do negative 5 times negative 2, right? Negative 5 times negative 2 to get positive 10, making that. Now, you say, that's great, Mr. Spate. What has this accomplished? I say, look. This says 2 times x squared times x minus 2 minus 5 times x minus 2. So this is a factorization, and this is a factorization. And if you're looking at that, you might notice, do they have a factor in common? And I would say, yes, student. They do have a factor in common, and that factor they have in common is x minus 2. This has an x minus 2, and this has an x minus 2. So what does that mean? It means you can factor out x minus 2 from both terms. So what's left? I say, well, if you factor out x minus 2, then you have 2x squared and minus 5. And so it is then 2x squared minus 5, and we are done. How nifty is that? That's it. We are done. Hooray! So, yeah. And now, sometimes I lose students here in class. They're like, Mr. Spake, I didn't quite get that. I say, now look, let me show you a similar example right off to the side. This example says 2x squared y minus 5y. And if I ask students, what is the GCF here? Most students immediately say, oh, well, they share a y, Mr. Spake. That has a y there and a y there. So you factor y out, and it's 2x squared minus 5. And I say, yes, correct. That is exactly how that works. But in this case, it's not y, it's x minus 2, right? So the same way you kind of pulled out these y's, you factor out a y from both terms, and then what was left was 2x minus 5, like this. It's the same thing here. You're lefting what we're sort of got 2x squared minus 5 right there. And that's why that works. Okay. So this is the grouping method. Let's do example B here. So I'm going to do grouping on this. And some students asked, do you have to group first two and last two? And I say, no, you don't. Because you can use the commutative property of addition as well. So I'm actually going to group this one. Here's 14x to the fourth plus 7x squared. I'm just choosing to group this one with this one because you can group these however you like. It doesn't matter. Although I would be careful. You usually want to do some combination of first and middle and middle and last. You don't usually, sorry for yawning, you don't usually want to do first and last in the two middle ones, okay? They don't always work out. And so then here's 12x cubed plus 6x like this. All right. So I'm going to say, all right, what's the GCF between these? 14x to the fourth plus 7x squared. 14 and 7, that's a GCF of 7. X to the fourth x squared, that's a GCF of x squared. And what do you got here? 7x squared times, 2 gets you the 14, and x squared gets you the x to the fourth. And then this is 7x squared times what is itself? That means you need a plus 1 there. And then same thing for the other one, 12 and 6, GCF is 6. And then x cubed and x share an x. And then you're left with 2x squared plus 1. And so just like that last example, they both share 2x squared minus plus 1. See, it's 7 times x squared times 2x squared plus 1. It's grouped together. It's a single factor plus 6 times x times 2x squared plus 1. Right? So what do they have in common? Well, they have 2x squared plus 1 in common. And so I factor that out. So it is 2x squared plus 1 times 7x squared plus 6x. Now, you might be inclined to say, oh, I'm done. And I would say, well, you did the hard part. Yeah, it's true. But is it completely factored? Well, not quite. 2x squared plus 1 is good. But notice 7x squared and 6x. Well, those still share something, right? this has an x squared, this has an x. That means they actually both share an x. Means you can take out that x, you can factor it out at the front. So you can say x times 2x squared plus 1. I'm not factoring out x from that. I'm factoring out x out from 7x squared, so that becomes 7x plus 6x divided by x is 6. And that is fully factored. This one was a little harder, and you might be, I know a number of students, when I show this one, they say, okay, I was doing great up to here. What's going on with that, though? Just remember that you can multiply in any order. So you can say 2 times 3 times 5 is the same as 5 times 2 times 3 is the same as 3 times 5 times 2 is the same as 2 times 5 times 3, right? It doesn't matter what order you multiply. So if you like, you could have written this answer as 2x squared plus 1, and then basically you're taking the x out from these, and you could put it in the middle. You could say times x, and then do 7x plus 6, right? But it just kind of looks nicer if you put the x in front. I mean, who says? I don't know. Me? I don't know. You don't have to. It doesn't matter. Yeah? You can put the x at the end. You can put it right here. It wouldn't matter. Just make sure it's factored out. Okay. 2 more student practice examples just to see this worked out, but not as much explanation. So for this one, I'm going to group the first 2 and the last 2. And the GCF of the first group is C, and the GCF of the second group is D. And so they both share A minus B in common, and what's left behind is C plus D. And that's done. I guess I should have said, hey, student, you should pause the video and try that one for yourself. Sorry, I should have said that. So here we go. We still have one more you can do. I say, hey, student, pause the video and see if you can try that one for yourself. Yeah? And then here's the answer. So I group x cubed plus 2x squared, and I group negative 3x minus 6. I say, okay, GCF time. Here's x squared, and then that's x plus 2, because that's it. That shared x squared. And then the other one shares a negative 3, so minus 3. And negative 3 times x, and then negative 3 times positive 2, gets you negative 6. Oh, so they share x plus 2, means it's x plus 2 times the other thing, x squared minus 3. And done. How nice is that? Oh, it's beautiful. My thumb's kind of hurting. It hurts to hold this iPad. You know, I just moved into a new apartment. So here's my new apartment, everyone. Oh, it looks like a little cottage, actually. It kind of looks like this. My new apartment, it looks like this. Something like that. It's got a little square here. But then we have a nice little circle window. It looks like this over here. And we have a little doorway right here. And then we have some steps that go up. And so now I'm in my game room, and I'm just filming a video, and it's just a good night. It's a great Tuesday on October 15th, 2024. Okay. That was my little mental break. Let's get back into it. So, factoring quadratic trinomials. This is the, bread and butter of this unit, in particular Unit 4, because the theme of Unit 4, or the focus of study, is quadratics. All that stuff we were just doing had nothing to do with quadratics. Now we're going to talk about quadratic trinomials. So, a couple things. We say quadratic trinomial. So trinomial means 3 terms, right? So ax squared plus bx plus c. That's 3 things being added together, 3 separate terms through addition. We know it's quadratic because the highest exponent term is x squared. Okay? If you had x cubed, well, that's cubic. The quadratic, the highest degree term, the highest exponent term is x squared. And a trinomial has 3 terms. Now, We can still do factoring maybe with, well, I guess we wouldn't really do it with quadratic monomials because they're just already a single thing. But you could do quadratic binomials, binomials meaning 1, 2. So, it's possible, actually, when we did GCF, right? So like x squared plus 2x, hey, that's a quadratic binomial where the GCF is x. And you say x plus 2 like that, right? So we did kind of do some of this. Now, the tricky thing about quadratic trinomials is the way you're able to factor these is using grouping, but you need stuff to group is the problem. So, if you say, oh, it's x squared minus 15x plus 36, well, are you going to group these two and then group this fella alone? I said, well, what are you going to do with that guy, right? There's nothing to do with him, really. Like, there's no GCF of, whenever we do GCF, we're trying to do it from multiple values, right? Like maybe 2 or more. GCF of a single number is, why would we be doing that, right? So if you can look at all the sort of practice we were doing, all of these had 1, 2, 3, 4 terms. You can do grouping with something like 5 terms, but right now we're just focused on like 1, 2, 3, 4. The problem with the trinomial is it only has 3. And so it would be really nice if we had 1, 2, 3, 4 terms somehow so we could do grouping on it. And I say, well, there is a way to do that. And the way to do that is we're essentially going to take this middle term and split it into 2 terms. Because if I can do that, I can say x squared plus blank plus 36, where these blanks sort of sum up to negative 15x. But I can't just break it apart willy-nilly. I can't just say x squared minus 10x minus 5x plus 36. This won't work. It has to be a specific sort of, I guess, decomposition so that your groupings work. And so here's how you do this. You draw this little X puzzle. And you might say, oh, I remember this. I did this in Algebra 1. And I said, yes, you did. Quadratic trinomials are of the form ax squared plus bx plus c. Now, in this little top, this little X puzzle or railroad tracks, whatever you call it, right? You say in the top goes A times C, front times back. And then in the bottom is B, or the middle term. And the goal is to find 2 numbers which multiply to get the top, but add to get the bottom. And so here's how this works. With this example, I say it's 36, so A times C, so it's 1 times 36, that's just 36, and the B value is negative 15. So now it's time to brainstorm. You've got the number 36. What are multiples of 36? Well, let's see. You've got 9 and 4. You've got 6 and 6. You've got 36 and 1. You've got 18 and 2. You've got 3 and 12, right? And so you consider all these multiples and you say, well, which multiples could I possibly use to get this negative 15 here? And I say, well, look at 3 and 12, right? Negative 3 minus 12 is negative 15. And if you did multiplication, negative 3 times negative 12 would get you positive 36. So what do we do with this information? I said, well, negative 15 is composed of negative 3 and negative 12. So that's how I'm going to break it apart. I'm going to say x squared minus 3x minus 12x plus 36. This is because this expression, negative 3x minus 12x, is negative 15x. And now I can do my lovely little grouping. I can say here's x squared minus 3x plus negative 12x plus 36. Now looking at this, I do GCF on both. GCF of the first group is x, getting me x minus 3. GCF of the other group is 12, but in particular, I would like the lead term to not be negative, so I'm going to factor out negative 12. Negative 12 would get me x, and then negative 12 times negative 3, right? Negative times negative is a positive. 12 times 3 is 36. X minus 3 is in common on both, and so I have x minus 3 times x minus 12. And we are done. Yay! And so that is trinomial factoring, right? Now the trick here was doing this little multiplication addition fact in order to break up a middle term into two terms. That way you had 4 things so that grouping would work out. By the way, if the grouping doesn't work out, you know it won't work out. Like, example, if this said x minus 3 and this said like x plus 2, well, then that would be different from each other, and so you couldn't factor that out. Okay. Next one. Same thing. A times c. I'm just going to do multiple of these. A times c up top. So you do 2 times 14 is 28. 11 on bottom. And so I say, okay, what two numbers multiply by 28? I get 11. So 28 is 7 times 4 and 14 times 2. And that's kind of it. You can do 28 1. But it should be pretty evident that it's 7 and 4. And so you're going to take 11x and split it into 7x and 4x, okay? Because it's this middle term here. So I say 2x squared plus 7x plus 4x plus 14, okay? And then you can group these. GCF of the first one is an x, and then you get 2x plus 7. GCF of 4 and 14 is 2, and that leaves you a 2x plus 7 again. So 2x plus 7 is the common factor that you can pull out, and what's left behind is x plus 2. And ta-da, we're done again. Woohoo. All done. There's my apartment. I'm up here right now. That's me. I'm in my little laid-back chair in my new game room. Okay. Filming videos for my Algebra 2 students. I love it. Okay. Some more examples. I'll brush through these, but we've essentially covered it. Okay. Factor out the trinomials. Hey, why don't you pause the video and try them, huh? Here's that one. You can pause and try it. Here's that one. You can pause and try it. All right. Let's go ahead and do that. A times c, 1 times negative 24. And then bottom b is negative 5. So what two numbers work? Well, I say negative 8 and 3. So I break this up as x squared minus 8x plus 3x minus 24. Group. And I'm going to do GCF. GCF again. And then they both have x minus 8 in common, leaving behind x plus 3. That's it. Pretty fast, right? And see how fast I did that? That is hopefully the goal. You may not be there right away, right now, but hopefully with enough practice with doing these, you'll kind of get there in time, yeah? Because it's not something you want to hesitate on. Like, you know, if you had this problem, you wouldn't want to take like 5 minutes on it, right? If you're taking 5 minutes on it now, it's fine. You're learning, you're building, right? But as we progress through the class, factoring something like this is just going to be a standard procedure. It's going to be part of a bunch of other math that we do, so it's something you want to focus on and get pretty good at, okay? Kind of like your times tables, you know? All right. Let's do another. A times c, so that's 6 times negative 3 is negative 18, and then negative 7 down on bottom. And so if I think of two numbers multiplying to get negative 18, I think negative 9 and 2 would work because those add to get negative 7. And so that's going to split up the middle term, 6x squared minus 9x plus 2x minus 3, right? GCF of the first, so if you had 6x squared minus 9x, GCF of that is just 3x, and you're left with 2x minus 3. But then the other one's just 2x minus 3, right? It's just this. And 2 and 3 don't share anything, and there's no variable stuff. So what's the GCF? 1. There is no real greatest common factor other than just the factor 1. So you can write, if you'd like to write a 1 there, right, you can put that there, and then what's left is you factor out 2x minus 3, and then what's left is 3x plus 1. And ta-da, our factoring is done. Fantastic. Fantastic. All right. We did it. Okay, we're getting there. I know, it's a lot of factoring. Thanks for sticking with me, guys. The next one is difference of squares. So these next two are called identities. So what an identity is in math, identity in math just means itself, right? It's identical to something, or equivalent, right? It's equal to itself. And so what's known as the difference of squares identity says that a squared minus b squared factors as a plus b, a minus b. This is a very, very easy algebraic equivalence to show, because look, here is a plus b times a minus b. We don't, who cares what a and b are? It's just some expression for distribution, right? If you distribute this, a times a is a squared, a times negative b is negative ab, b times a is positive ab, and negative b times b is negative b squared. And you'll notice that negative ab plus positive ab eliminate each other. They sort of cancel out, become 0, and I'm left with a squared minus b squared. So what this does is it basically shows, hey, if you ever see this, if you ever see something called a difference of squares, you can factor it immediately using this identity, which says it's a plus b, a minus b. Okay? Notice how I pointed the arrows at what I was saying verbally. It is a difference between square numbers. Yeah? A squared minus b squared. Difference, minus, subtraction, difference between squares, a squared and b squared. Yeah? Okay. So, we love difference of squares. It's very easy to use and pretty easy to recognize if you know your perfect squares. So perfect squares, for example, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, and then keep going, 25, 36, 49, and so forth, right? So, if I look at example 1, what the difference of squares identity says is a squared minus b squared factors as a plus b, a minus b. You could just sort of shortcut this factoring. If I look at x squared minus 25, that's x squared, perfect square, minus, well, 25 is special. 25 is 5 squared. So the way this factors is your x is like that a and your 5 is like that b. So this x is that a and that 5 is that b. Meaning it factors as x plus 5, x minus 5. And that's it. You're done. You factored it. It's called the difference of squares identity, and you are done. Because that's fully factored. Yay. So look at the other one. Here's 4x squared minus 81. Why do we like 4? Well, 4 is 2 squared, right? So this is like saying 2x getting squared, because 2x times 2x is 4x squared. 81 is like 9 squared, because it's perfect square, right? And so this would factor as a plus b, a minus b, where a is 2x, So it's 2x plus 9. 9 is like the b. And 2x minus 9. And we're done. Right? Now see, you can do all that quadratic, like trinomial factoring business. You could do 4 times 81, which is, oh sheesh, what is that, guys? What's 4 times negative 81? Is it negative 324? Oh my gosh. And then that's 0. So what 2 numbers multiply to get negative 3? What? Get out of here. This is way easier, right? Recognizing difference of squares is very effective. Okay. Another couple examples. So student practice, if you'd like to really try this one, pause and give these 2 a go. Here are the answers. X squared minus 16 is like saying x squared minus 4 squared, which means its factors is x plus 4 and x minus 4. And you're done. And then the other one, 25x squared is like saying quantity 5x squared minus 1 squared. And so how this factors is 5x plus 1 and 5x minus 1. And so that's your difference of squares there. Okay. One more to go. One more, guys. We're doing wonderful. It is a long video, but it's an important video, right? If anything, it's the most important video of the whole year, right? Okay. Perfect square trinomials. Okay. I like this one, but it's a little hard to see. And it's okay. This one might take some of you some practice, like some real practice and work at, kind of memorizing and recognizing. It's not so much the memorizing, it's more so the recognizing. When am I allowed to use this? When is this useful, right? So kind of like, it's also called an identity, just like difference of squares. But a perfect square trinomial, basically, if you took a square of a binomial, so a plus b quantity squared, that means a plus b times itself, right? And if you carry out the distribution here, you're going to get it up. You're going to end up with a squared, and you'll do ab and then another ab. So that's double 2ab, and then it ends with b squared. And this is just basic distribution, right? This, when distributed, is this trinomial. So the reason it's called a perfect square trinomial, see the words there? Perfect square trinomial. I say, well, trinomial because it's 1, 2, 3 terms, but it's called a perfect square trinomial because when you take these 3 terms and factor it, you get the same 2 factors, right? You get a plus b times itself, and whenever you multiply something by itself, that just means you're squaring it, so it's called a perfect square because it's an expression that's written as a square. Now, the trick to this, and I should say it also carries for minus, so apologies. If you say a squared minus 2ab plus b squared, then this factors as a minus b squared. Okay, just a quick little hint there. Both b squareds are positive. The only thing that's different is the plus and minus right there. Okay, plus goes with plus, minus goes with minus. Okay. Now, let me try these out. So, as I was just kind of saying, the trick is, let me write this here for you. It's ax squared a squared at the front, b squared at the back. So you're thinking, do I see perfect squares in the first term and last term? This would be my first signal. So if I look at letter A, x squared, that's a perfect square, and 1 squared, that's a perfect square. So, okay, this is beautiful, right? Now, the next thing to look at is if you took like the square root of both those things. So the square root of a squared is a, the square root of b squared is b. If I took the roots of both of those and I just said, oh, okay, what's ab? And I double that, then that follows this pattern, right? The one that's sort of laid out here. If the middle is double of a times b, then it will factor like this. Now, if it's not double, it doesn't do that. It has to specifically be 2 times AB, okay? But we're safe on this one because I say, well, what's A? A is X, so it's 2 times X, and then this one's just a 1, right? And so the way this is written is x squared minus 2x times 1 plus 1 squared. And so this follows this pattern right up here where this is minus and this is plus, right? X squared correlates with a squared. These negatives correlate. 2a, b, and 1 goes with b squared. So you see they're all sort of matched up, right? And this factors as a minus b getting squared. So then this would factor. My a in this case is like x, and my b in this case is like 1, so it's minus 1 squared. And so that's how you use a perfect square trinomial pattern to factor. It's not the end of the world if you don't recognize this one, but there might be questions that are going to be a headache if you don't see this. And by headache, I mean letter B. Because if you wanted to solve this trinomial using typical factoring with like an X puzzle, because you can do an X puzzle. You can do 9 times 25. What the heck was that? 225, and then this is 30. And so if you want to do that, I mean, that's fine. It'll work. But I'm just going to say, okay, look. 9 and 25, hey, those are perfect squares. This is a pretty good thing to notice. 9 is 3 squared. So 9x squared is 3x quantity squared. And 5 squared is 25. Now, if you took 3x times 5, that would get you 15x. And if you double that, you get this 30. So it's quantity 3x squared plus 2 times 3x plus 5 plus 5 squared. This follows the a squared plus 2ab plus b squared pattern, which means this factors as a plus b squared, where a is like 3x and b is like 5. And so we are done. 3x plus 5 quantity squared. Again, this is called a perfect square trinomial. Okay, there are 2 more practice problems for the end of this video. You're welcome to pause and try them out. Go ahead, do so. And now I'm going to walk through these real quick. Letter A, so it's x squared at the front, perfect square. 36 is 6 squared at the end, so this is a good sign. And the middle, if I take 6 times x and I double it, oh, hey, this is again a squared plus 2ab plus b squared, right? Meaning this should factor as x plus 6 squared. Good? And then one more, and that's letter B, which says 4x squared minus 4x plus 1. 4 is 2 squared. So 4x squared is 2x quantity squared. This is, again, that 1 squared, kind of like we saw earlier over here with the option A. So then I say, okay, well, that's 2x, so that's 2x. That's 1. And if I double it, yeah, okay, doubling it does get me 4x. And this is minus. So this is like my A, and that's like my B. So it should factor as A is 2x, and then it's minus, and B is 1. And so then that thing is squared like so. And there you have it. That is the perfect square trinomial factoring pattern. So, we've made it to the end of the video. Wow, thank you so much for sticking with me. I'm not even sure. It was probably an hour long, maybe more. I hope it wasn't more, guys. I hope I did this in less than an hour. And there it is. So, those are the 5 factoring techniques. We're going to use these throughout the unit. In particular, the one that we're really going to focus on a lot of the time is quadratic trinomials. That's the big one in Unit 4 because we're talking about quadratics. When we get to Unit 5, a lot of these factoring techniques are going to come back and just be very useful for other polynomials. So, there it is. Hope you enjoyed the video. Take care. Have a good night. Get some sleep if you're staying up late. And I'll see you around.